Hello dear students, let us continue our discussion on group theory. So in the last lecture actually I had by mistake repeated the lecture of the previous class. The uniqueness of identity inverse, actually I had already discussed that, so sorry for that, I did not remember that I already did it. Okay, so in today's lecture we will continue with our examples, some more examples of groups. Okay. So one exercise probably which I had given was for you to verify or to show that this set 1 minus 1 I minus I. Okay, these are the fourth roots of unity is a group with respect to multiplication. Okay, just ordinary multiplication. Okay. So you can show this using the help of composition table. Okay, so I'm just showing you how to do it. So just similar to whatever we have done it for omega. Right. Omega square, 1 omega square, that problem was there. So we construct this composition table. So here in each column we will write the given numbers, and in each row also we will write the given numbers, and then we will try to compose them. Okay, compose means you will just try to find out the sum. So here the operation is multiplication. We will mention the operation in this top left corner. Here we will write the elements 1 minus 1 I minus I. Okay. Here also we will write 1 minus 1, this is I minus I. Okay, and then we will multiply this row with column. So first element of the first row is multiplied with first element of the first column. So 1 into 1 is 1. Okay, so here actually what we are doing, since it's a finite set, we are just finding out the products of each element with every other element. Okay, to see if the closure property is satisfied. We can also conclude about the associative property from the commutative property from here itself. Okay, so 1 into 1 is 1, 1 into minus 1 is minus 1, 1 into I is I, 1 into minus I is minus I. Okay, minus 1 into 1 is minus 1, minus 1 into minus 1 is 1, minus 1 into I is again minus I, and minus 1 into minus I is I. Okay, I into 1 is I. Okay, I into minus 1 is minus I into I is I square, as you know is minus 1, I into minus I is minus I square, so that is 1. Okay, so minus I into 1 is minus I, and then minus I into minus 1 is I, and then minus I into I is minus I square, that is actually 1. Minus I square is actually 1. Okay, so this is 1, and minus I into minus I, that is I square, so that is actually minus 1. So in the composition table, one thing you observe that there is no repetition of any of the elements in any row or column. Okay, so here 1 appears only once in this particular row. Each element appears exactly once. Okay, actually there cannot be any repetition in this composition table. We can prove it actually, right? So if say the A is one element, and here there are elements B and C. Okay, suppose in this particular row there is a repetition, say A star B is same as A star C. Okay, so why there cannot be repetition? Because A star, if suppose there is a repetition, A star B equal to A star C, then in the last class also we had done the cancellation law will give us B equal to C. That means whenever B and C are unequal, this A star B and A star C can never be equal, because whenever they are equal, this actually by cancellation law it implies that B and C also should be equal. Okay, so there cannot be any repetition in the composition table. Okay, if you have a look at the columns also, there cannot be any repetitions. Right, in each column there cannot be any repetition. Okay, so if you find some repetition somewhere, then you should understand that your calculation is incorrect. Okay, So from this table what we see that, say, let us name this set as G. Let G equal to 1 minus 1 I minus I. Okay, so from table we see that G is closed, or G cross is closed. Okay, closed. So closure property is satisfied, and the other properties will be satisfied because of the associative property is satisfied because these are just complex numbers. Okay, and since G is a subset of, or we can write it this way, since multiplication of complex numbers is associative, since multiplication of complex numbers is associative, so G cross is associative. Okay, or G is associative with respect to cross. Okay, so associative property is already there, right? And then we can talk about the identity element. So here you see which element multiplied with every other element gives the respective elements. Okay, so that is actually 1. From the first row you can see 1 multiplied with any other thing gives that particular thing. Okay, 1 multiplied with any other thing, this gives any other thing. Okay, so it's very simple. So here also 1 is the identity. Okay, identity element also. And what is left? Inverse. Okay, what is 1 inverse? 1 inverse is 1 minus 1 inverse. If you see, minus 1 inverse is what? From the table itself you can see minus 1 multiplied with which element gives us 1. So minus 1 multiplied with minus 1 gives us 1. Okay, so it's inverse of minus 1 is minus 1. Okay, I inverse. So here this inverse doesn't mean 1 by. Okay, when I write this one inverse, it's just the inverse element of A. So since we are dealing with complex numbers, ultimately it's same as 1 by I. Okay, but in general it's not true. So you have to understand that it's the inverse element in the group. Okay, so 1 multiplied with which element? I multiplied with which element gives you 1? So it's minus I. So inverse of I is actually minus I. Okay, I inverse is minus I, and minus I inverse is actually I. So these are the inverses of each element. So therefore G star cross is a group. Okay, and from the table also you can see that it's a symmetric matrix. If the composition table is a symmetric matrix, okay, this A11 equal to A1. So this is in form of a matrix, right? So if it is a symmetric matrix, then it is actually the operation is commutative. Okay, see here I 1 is 1 and I are same. This I and this I is same. This minus I is same. Okay, this one they are same. Okay, so if it is a symmetric matrix, then it's commutative. Okay, G is a group. Also from the table we see that star cross is commutative in G. Okay, so there not only G star is a G cross is a group. G cross is actually a abelian group. Okay, it's an abelian group. Okay, so this is one exercise. So these are quite simple. Okay, next we can also show the nth roots of unity. They form a group with respect to multiplication. Okay, so we can show that the set of nth roots of unity nth roots of unity form a group with respect to multiplication of complex numbers. Okay, multiplication of complex numbers. Okay, this also can be shown. So what are the nth roots of unity? Nth roots of unity means the solutions of the equation, say x to the power n equal to 1. X to the power n equal to 1, the solution of this solutions of this equation are called nth roots of unity. Say for x n equal to 2, x square equal to 1, what are the 2th roots of unity or the square roots of unity? These are minus 1 and 1. Okay, x cube equal to 1, what are the solutions? 1 omega square. Okay, x to the power 4 equal to 1, the solutions are 1 minus 1 I minus I. Okay, these are the solutions. So these are the 4th roots of unity. Okay, 1 omega square, they are the cubed roots of unity. Okay, similarly there are 5th roots of unity, 6th root, any nth root of unity we can find it out using de Moivre's theorem. Okay, so which was there in trigonometry, but I think in the new CBCS course you will get classical algebra only in the SEC paper. So if you are having DSC with BSc with mathematics, means in the past course, then you will get this classical algebra portion. Okay, so there you have de Moivre's theorem. Anyways, in higher secondary also probably this was taught, de Moivre's theorem, that if you have cos theta plus I sin theta whole to the power n, where n is a integer, then you can write it as cos n theta plus I sin n theta. Okay, this can be written. And if n is a rational number, then of the form say, or say if I say like this, cos theta plus I sin theta to the power 1 by q. Okay, or the qth root of this. So that this then cos, one of the values of this, one of the values is cos theta by q plus I sin theta by q. Okay, so there are other values as well which are denoted by so actually cos twice pi r plus theta by q. Okay, this plus I sin twice pi r plus theta by q. Okay, this is the general expression where r varies from 0, 1 to up to q minus 1. If r is q, then there is a repetition. Okay, if r is exactly equal to q, there is a repetition of this, right? So r varies from 0 to q minus 1. So there are q roots, okay, q values for which this happens. Okay, so these are part of trigonometry. Okay, so we will require this to solve to show that the nth roots of unity, they form a group with respect to this multiplication. Okay, so let g equal to 1, so let us use one symbol like say z square, z cube up to z to the power n minus 1. Okay, so why I have written this, I'll show you. This be the set of nth roots of unity, nth roots of unity. Okay, so what is this? Actually I told you this cos theta plus I sin theta to the power 1 by q. Okay, then cos theta by q plus I sin theta by q is one of the values of this expression. Okay, and this cos theta plus I sin theta actually can be written as cos, by your properties of trigonometry, it's twice pi r plus theta plus I sin twice pi r plus theta. Okay, so one of the values of this, the q values of this cos theta plus I sin theta to the power q are given by this expression. Okay, earlier I had made a mistake that twice pi r plus theta by q I had written, not that one. It's twice pi r plus theta by q. Okay, and for r equal to 0 on top to q minus r. For r equal to q there will be a repetition. For r equal to q it will become 2 pi plus theta by, for r equal to 0 it is cos theta by q. Okay, for r equal to q this value will be cos 2 pi plus theta by q. Okay, which is actually same as theta by q only, cos theta by q only. Okay, so these are the values actually. So you see, the interesting thing is that each of these values satisfy one property, that the nth power, if we take the nth power, then the value that we get is actually 1. Okay, right. So for nth root of unity, x to the power n has to be equal to 1. Okay, all solutions of this equation are said to be the nth roots of unity. Okay, so how can I write x to the power n means the nth root of unity in this form, cos theta plus I sin theta? How do I write it? 1 can be written as cos 0 plus I sin 0, right? 1 can be written as this. Okay, and then we can write the other values as somewhat using this 2 pi r equal to 1 to 2 pi by n cos 2 pi by n plus I sin 2 pi by n. Okay, this is the second value, right? So if n is suppose 3, it's cos 2 pi by 3 plus I sin 2 pi by 3. Okay, so only one of them is the real root of unity. Okay, the others are complex roots. Okay, but even then all of this satisfy the property that if I take the nth power, then apply Inverse theorem, so this n will come here. So cos n into 2 pi by n plus I sin n into 2 pi by n, so that will be cos 2 pi plus I sin 2 pi, that is again equal to 1. Okay, so the nth power is 1. So we are not going into so many complications here, just it was to introduce you to this general form of writing. Okay, we will in fact not require exactly these things in our proof. We can work with only this property, that x to the power n is equal to 1. Okay, so means if I know one of the complex roots, then all other complex roots can be written as powers of this z. Okay, so z is one complex root, all other complex roots can be written as powers of z. Okay, why is, you see, just say 2 pi by n plus I sin 2 pi by n, this is one complex root. Okay, the next complex root will be this square of this. Okay, so square of this is cos 4 pi by n plus I sin 4 pi by n. Okay, 4 pi by n. Then the next complex roots will be cube of this, so 6 pi by n plus I sin 6 pi by n. Okay, so that way it will go up to your n minus 1. Okay, so when it is n, there will be a repetition, it will give us back the real root, that is 1. Okay, so all solutions of this x to the power n equal to 1, these are the elements of this particular set. Okay, so be this a set of nth roots of unity where z is a fixed complex root. Okay, fixed complex nth root, because that is not real nth root. Thus z to the power n is always equal to 1. Okay, this is always satisfied. Okay, so and 1 can be written, this 1 can be written as z to the power 0. Okay, so this one I can write this one as z to the power 0. Okay, so now I have to check the closure property, that if I take two elements from this G, whether it will satisfy, means whether I'll get an element inside G only. Okay, so let z to the power I comma z to the power j belong to G be any elements. Okay, be any elements. Right, so any element inside G is of this form, z to the power I, z to the power j. Okay, so here, so this I should be less than or equal to, greater than or equal to 0 and less than or equal to n minus 1, and this j also should lie between 0 and n minus 1. Okay, so now I have to multiply this two. Okay, we have to multiply this. So now z to the power I into z to the power j. Okay, so I have to show that this is also an element inside the set G. Okay, so but what is z to the power I into z to the power j? It is actually z to the power I plus j. Okay, but I means from here directly I cannot say that it belongs to G, because I plus j may be greater than n also. Okay, if I is something like say n by 2 and j is something like n by 2 plus 1, okay, or n by 2 itself, then I plus j is exactly equal to n. Okay, but the powers here inside G, the powers of z inside G are less than or equal to n minus 1. Okay, so I plus j need not be less than or equal to n minus 1, it may be greater than or equal to n. So we have to separate that thing. So for that I will use something called division algorithm. Okay, so by division algorithm, so what happens, you see, I will give you an example. Suppose your n is say 7. Okay, and so z to the power 3 is an element inside G, right? And z to the power say 6, that is also an element inside G. Okay, but if I multiply z cube with z to the power 6, then what I'll get z to the power 3 plus 6, that is z to the power 9. Okay, but z to the power 9, by the way I have written G, it is not obvious that it is inside G, because G will contain, what are the elements G will contain? Z to the power 0, z to the power 1 up to z to the power, here n is 7, so up to z to the power 6. So z to the power 9 is not an element inside G, but we can actually show that it's actually an element. Why? Because z to the power 9 can be written as z to the power 6 plus 3. Okay, so z to the power 6 into I can write this one as z to the power 7 plus 2. Okay, so z to the power 7 into z square. But what is z to the power 7? Z to the power 7 is 1, because I am considering the 7th roots of unity. Okay, so z to the power 7 is 1, so this is just 1 into z square. Okay, so here what I have done, I have divided 9 by 7 to get remainder 2. Okay, so 9 can be written as 7 into 1 plus 2. Okay, right. So if it is something like z to the power 6 into z to the power 6, so in that case I will get z to the power 12. Okay, so how do I work with it? Z to the power 12 I will again divide by 7, so 7 ones are 7, and then this is remainder is 5. So z to the power 12 can be written as z to the power 7 plus 5, so this will be z to the power 7 into z to the power 5. So z to the power 7 is 1, this is ultimately z to the power 5, which belongs to G. Okay, we are sure it will belong to G. Okay, so this is how we will carry out the multiplication of z to the power I into z to the power j. Okay, so let us try that. So what I'll do, I'll divide I plus j by n. Okay, so by division algorithm division algorithm there exist integers q and r such that I plus j can be written as n into q plus r, where r lies between 0 to n minus 1. Okay, so therefore z to the power I into z to the power j, this will be actually z to the power nq plus r. So this is z to the power nq into z to the power r. But what is z to the power nq? Z to the power nq can be written as z to the power n whole to the power q, so into z to the power r, right? And this can be written as 1 to the power q into z to the power r. So this is just z to the power r, where r is lying between 0 and n minus 1. So this actually belongs to G. Okay, so ultimately I have shown that z to the whatever be the value of I and j, z to the power I into z to the power j is always an element inside G. Okay, so G is closed with respect to multiplication. Okay, so you try to understand this. I plus j is equal to nq plus r. We can write using division algorithm. So z to the power nq plus r can be written as z to the power nq into z to the power r. So it is z to the power n whole to the power q. But z to the power n is 1 because we are considering nth roots of unity. Okay, here we have written z to the power n is equal to 1. Okay, so from there itself we have got this one. So closure property is satisfied. Associative property will be satisfied because these are complex numbers. Since G is a set of complex numbers, so G is associative. With respect to multiplication. Okay, with respect to multiplication, it's an associative set. Okay, G is associative with respect to multiplication. Then I have to find out what is the identity element. So 1 belongs to G is the identity. Okay, is the identity. Okay, because 1 multiplied with z to the power I is just z to the power I, as 1 multiplied with z to the power I is equal to z to the power I for all z to the power I inside G. Okay, so 1 is the identity, and for z to the power I inside G, for z to the power I inside G, the element z to the power n minus I, okay, is the or satisfies z to the power I into z to the power n minus I. What is that? This is equal to z to the power I plus n minus I. Okay, what is that? This is equal to z to the power n, which is equal to 1. So that means what? Z to the power n minus I is inverse of z to the power I. So therefore z to the power n minus I is inverse of z to the power I in G. Okay, so all properties are satisfied, and also it's commutative. Okay, also multiplication of complex numbers is commutative. Multiplication of complex numbers is commutative. Okay. Commutative. So G with respect to multiplication is an abelian group. Okay. Is an abelian group. Okay, so the set of nth roots of unity forms a group. No, not only group, it's an abelian group. Okay, forms an abelian. Let me just write it in the question itself. Forms an abelian group with respect to multiplication of complex numbers. Okay, so this is one more example of group. Okay, another example which you may try to think about is the set of This also I had mentioned in the earlier classes also, the set of rational numbers non-zero rational numbers. Okay, non-zero rational numbers with respect to multiplication. Okay, this is a group. Multiplication is a group. Okay, it's a group. So you try to complete these things. The set of non-zero real numbers. Okay, non-zero real numbers with respect to multiplication is a group. Okay, so these are some of the exercises. So in the next class I'll discuss about the groups which can be formed with matrices. Okay, thank you.